Okay, so since we've looked at surface integrals for scalar functions, and we said we would be thinking about surface integrals for scalar and vector functions, we're going to move on to that more complicated vector function approach. And this is sort of the last type of integral we learn in class, so I know it's really challenging. And I want you all to just kind of like take a moment and think about how we set up the surface integral for the scalar function and how it hopefully felt very familiar from when you learned how to compute surface area. And so surface integrals for vector functions are just going to be one step further than that. There's just going to be a little bit of extra trying to sort of get rid of the vector component, just like there was for line integrals. So we're going to do our best, but it's okay if it takes a while to figure out. Okay, so the first tricky part of most of these problems is going to be identifying all the different pieces. So you're going to have to identify the surface S. And I'm going to write these steps as if we're thinking about Cartesian coordinates because we'll be doing that the most often. And you're going to want to identify that as something that gives you the coordinate z in terms of functions x, y. We've learned a lot how to plot things like that. Here's like z equal to x squared plus y squared. So your g of xy would be x squared plus y squared. For example, that's a thing you know how to plot and a surface that you're pretty familiar with. I'm going to erase that though, because I don't want you to think that you can only do this for that type of surface. Okay, and then you're going to have to identify the region R below surface. So that's a 2D region that describes kind of the shadow of your surface, exactly the same way as we did for surface area problems. Widest area of your surface, just like we did when we have like intersecting surfaces for 3D integrals. So this is a thing we've done a lot before, and I know it's still tricky, but at least you know what it is. And then, let's see, you've got S, you've got R. So identifying the function f could be a little bit like tricky because it could look like your surface because they're all scalar functions. Identifying your function of vector f is easier because it tends to be the only vector you were given. But remember, when we identify it, we have to make that substitution where our goal is to turn this into a 2D integral. So we do have to get rid of any 3D variables that we have. So for example, you could get rid of z using g of xy from your surface. And then you're going to compute the normal vector for the surface, which is just going to be to look at negative g sub x, negative g sub y, 1. And I'm sorry, I'm just realizing that I used F here when I should have used G. So hopefully you all caught that at the time. We'll make a big point of talking about that at the start of lecture. Make sure everyone's notes are corrected. I did it correctly in the example, but that's okay. So compute n for the surface. This uses the same components as our surface area formula because our surface area formula is exactly the same as this. And then you're going to compute f dot n. Using your f where you've replaced z so that there's no z in the formula. So this is just taking a dot product. What we're looking for is sort of the components of f that run with the normal vector. So this goes back to the idea that the surface integral tells us about f perpendicular to the surface. When we take that dot product, that's what we're selecting for. And then you can go ahead and evaluate over the 2D region R your f dot n over whatever dA you have, dx, dy, could convert to polar, anything you want. But this is going to give you a scalar function. This is a 2D integral, and so that's something you know how to do. Yeah, okay. I just want to go back to the original steps for the scalar surface integral real quick. So that if you didn't see what I was doing before, all I did was I had originally used f for my surface function and f for the thing inside my integral when I wrote these steps. So you just have to use a different function. I picked g for surfaces to do all the surface related stuff. And the example's fine. It's just these steps in your notes you need to go back and fix.